Hi everyone! Before we get into the work kinetic energy theorem, I want to take a minute to talk about kinetic energy. So kinetic energy is the energy that an object has that's associated with its motion. So any object that's moving has kinetic energy. The symbol for kinetic energy is Ke, and it's equal to 1/2 mv squared. So kinetic energy is a scalar quantity like all types of energy, and it's measured in joules. Then we have the mass in kilograms, and v is the speed in meters per second. So let's do some simple examples with kinetic energy. Example 3, calculate the kinetic energy of a 1500 kilogram car traveling at 5 meters per second. Suppose the car speeds up to 10 meters per second. What is its change in kinetic energy? Okay, so to start, it's simple. We're just plugging into the definition for kinetic energy. Ke equals 1/2 mv squared. So that's 1/2 times 1500 kilograms times 5 meters per second squared, which is 18,750 joules. Now that same car speeds up to 10 meters per second, and we want the change in kinetic energy. So like any other variable, the change is the delta symbol. So delta Ke equals Ke final minus Ke initial. So this is 1/2 m v final squared minus 1/2 m v initial squared. We've already found this initial kinetic energy term now. It's this at 5 meters per second. So we can just calculate the final 1/2 1500 kilograms times 10 meters per second squared minus 18,750 joules gives 56,250 joules. I also want to point out that if we hadn't found this initial term already and you wanted to just find the change in kinetic energy, it can also be written like this, 1/2 m v squared minus v naught squared. So we can factor out the 1/2 m from this expression. However, what we can't do is write 1/2 m v minus v naught squared. That's not mathematically the same, right? So just be careful that you're factoring out 1/2 m properly if you do want to simplify that expression. Example 4, what is the mass of a ball that has kinetic energy of 1200 joules when it is moving at 14 meters per second? This is another quick example. So we have the kinetic energy and the velocity, and then we need to find the mass. So I'll just rearrange here. We have m equals 2 Ke over v squared. And so that's going to be 2 times 1200 joules over 14 meters per second squared, which is 12.2 kilograms. The work kinetic energy theorem says that the net work done on an object is equal to its change in kinetic energy. This means that the net work done causes a change in kinetic energy. So if we have overall a net positive work done, that's an increase in kinetic energy, whereas overall if the net work done is negative, that's a decrease in the system's kinetic energy. And remember that we have two ways of calculating net work, so we can either use the sum of all the works done by the individual objects or the net force and use F net d cos theta to find the net work. Then the change in kinetic energy is equal to delta Ke, which is Ke final minus Ke initial. And this is a really useful theorem because it provides a direct link between the net force acting on the object, so the dynamics, and its change in speed. So some of the problems that we'll see in this section we have solved before. We've solved similar problems using dynamics and then kinematics to find the final velocity, or the other way to use velocity information and then to find the acceleration and the forces. So this is another way to solve those problems using the energy approach. Okay, I'll insert the derivation here. I'm going to take a minute to prove the work kinetic energy theorem. I like this proof because it's something that you can do yourself with the simple kinematics and dynamics formulas that we've already learned. So let's consider an object that's moving in one dimension along the x direction and experiences a net force in that direction as well along the surface. So it's accelerating along the surface. Then the work done, the net work, is equal to F net d cos theta. So one thing I want to plug in is that F net equals ma. So we have ma d cos theta. Also, we are considering the case where the net force is parallel to the displacement, so we'll have cos of 0, which equals 1. So we're at net work equals ma d. So now I want to use a kinematics equation to eliminate this d factor here. So I'm going to choose v squared equals v naught squared plus 2ad. So we have d equals v squared minus v naught squared over 2a. And I'm plugging that in here for d. So the net work equals ma v squared minus v naught squared over 2a. And you can probably already see where this is going now. So I'm going to cancel these factors of the acceleration. And then I have this factor of 1/2, so 1/2 m v squared minus v naught squared. So the net work equals 1/2 m v squared minus 1/2 m v naught squared, which is ke final minus ke initial. So we have the net work equal to the change in kinetic energy. And though I assumed that this was in one dimension along the x direction, this is always true for the net work done on the object. And we can see that a positive increase in the net work means an increase in kinetic energy to the system, whereas a negative value for the net work done would mean a decrease in kinetic energy to the system. This also means that if the net work done on a system is 0, the kinetic energy will remain the same. There's no change in the kinetic energy in that case. Now let's try some examples. Remember that it's always the net force that goes into the work done in the work kinetic energy theorem. Example 5, A, find the thrust force required to give a 200 kilogram rocket an acceleration of 0.10 g upwards. B, determine the net work done by the forces on the rocket as the rocket ascends 100 meters. And C, if the rocket started from rest, what is its final speed at the 100 meter mark? Okay, part A is really just a dynamics problem. We know that the rocket has to have an acceleration of 0.10 g upwards. So we can use the net force in order to find the thrust force, which is the applied force here. So I have Fa minus Fg equals ma. So then Fa equals ma plus Fg, which is ma plus mg. And I'll plug in this acceleration now since it's in terms of g's. So that's m times 0.1 g plus mg. We can collect like terms. I have 1 plus 0.1. So 1.1 mg, which is 1.1 times 200 kilograms times 9.8 newtons per kilogram to give 2,156 newtons for the thrust force. All right, now for part B, we want the net work done. Remember, there are two options in order to find the net work done. We could either add up the work done by each force acting on the object, or we can use the net force. Since we have the acceleration this time, I will just use the net force. So the net force, F net, equals ma. It's in the y direction this time. So this is going to be 200 kilograms times 0.1 times 9.8 meters per second squared, or newtons per kilogram, since we have an acceleration of 0.1 g's. Okay, and that is 196 newtons. So now we can plug that into our network equation. The network is F net d cos theta. This will be cos of 0 since the net force is directed in the direction the object is accelerating, which is up. So the net force is parallel to the displacement. That's 1. So this is just F net d, which is 196 newtons times 100 meters. So we get 1.96 times 10 to the 4 Newton meters or joules. All right, lastly, the question is, if the rocket started from rest, what is its final speed at the 100-meter mark? So I know you can solve this using the acceleration and kinematics, but let's solve using the work kinetic energy theorem. So we want to use the net work equals delta KE, which is KE final minus KE initial. We're told that the rocket starts from rest, so KE initial is 0. So our net work is going to equal 1/2 m v final squared, the final kinetic energy. This means that v equals the root of 2 times the net work over the mass. And now we can plug the numbers in, so v is the root of 2 times 1.96 times 10 to the 4 joules over 200 kilograms. So 14 meters per second when it reaches that 100-meter mark. Example 6, a 200-gram ball is lifted upwards from rest by a string. The tension in the string is 2.35 newtons. What is the ball's speed after it has moved upwards by 1.75 meters? This is another work kinetic energy theorem problem since we're looking for the speed after work was done. Again, we can solve by dynamics and kinematics, but we're going to use the work kinetic energy theorem. So the ball is lifted upwards from rest, so we have final kinetic energy minus initial kinetic energy, which is 0. So we'll have the net work equal to the final kinetic energy. So let's find the net work first since we have the displacement and the forces acting on the box. I'll find the net force and do it that way. Again, the other way is to find the work done by each force and then to add them all up. So I have the net force equal to Ft minus Fg. So 2.35 newtons minus mg, 0.2 kilograms, times 9.8 newtons per kilogram is 0.39 newtons. Then the net work is the net force, F net d cos theta. Again, in this case, the object is moving up and the net force is upwards as well since we ended up with a positive value here. So this is cos of 0. They're in the same direction, which is 1. So it's just F net d, 0.39 newtons times 1.75 meters, which is 0.6825 joules. Alternatively, you can leave this as F net d and plug it into the work kinetic energy theorem. But now that we have that, we can find the speed. So the net work equals the final kinetic energy, 1/2 mv squared. So v equals the root of 2 times the net work divided by m. So that's going to be the root of 2 times 0.6825 joules over 0.2 kilograms, which is 2.61 meters per second. Example 7, a 62-kilogram baseball player starts to slide into third base. She is initially moving at 5.5 meters per second when she starts to slide, and she comes to a stop in 2.5 meters. A, what was the kinetic energy of the player before she started to slide? B, what was the change in kinetic energy during the slide? C, how much total work was done on the player? D, what was the magnitude of the frictional force and the coefficient of kinetic friction? So I've drawn out the free body diagram here. There's the normal force and the force of gravity acting on the player, and the force of kinetic friction. So she's just sliding. There's no applied force here, only friction that is slowing her down, and it's over this 2.5 meter displacement. She's starting with 5.5 meters per second for velocity and then coming to a stop at the end of the 2.5 meters. All right, so A asks for the initial kinetic energy, Ke naught, 1/2 mv naught squared. So 1/2, 62 kilograms times 5.5 meters per second squared, which is 938 joules. Okay, then for B, we want her change in kinetic energy during the slide. Delta K is Ke final minus Ke initial. And this time we know that Ke final is 0 because she is coming to a stop. So that's 0. So it's just negative Ke initial, which is negative 938 joules. All right, and then for part C, what is the total work done? We know that the net work done equals the change in kinetic energy. So it's really just getting us to recall that work kinetic energy theorem. So she loses 938 joules of kinetic energy, which is the work done, as she comes to a stop. All right, now for finding the friction force, Fk, and the coefficient of kinetic friction, mu k. We're going to need the normal force, so in the y direction we have the net force equal to 0. There's no acceleration in that direction. So Fn equals Fg, which is mg here. And then kinetic friction, Fk, is equal to mu k Fn. So we can plug in mu k mg. All right, and that is also going to be the net force because in the x direction because there's only one force acting in the x direction there. So our net work is going to equal the work done by kinetic friction this time. And this is going to be equal to the force of kinetic friction, d cos 180, since they're in opposite directions. And we'll always find this for friction since friction acts anti-parallel to the displacement. So negative Fkd. So we can find this force of friction. It's going to be negative of the net work done divided by the displacement. So that's negative of negative 938 joules divided by 2.5 meters. So 375.2 newtons. And that's one of our answers. That's the force of kinetic friction. Lastly, we want the coefficient of friction. So I have, going back to this relationship here, Fk equals mu k Fn, which is mu k mg, I'm going to solve here for the coefficient. So we'll have mu k equals Fk over mg. Okay, move that up. So Fk was 375.2 newtons divided by the mass, 62 kilograms, times 9.8 newtons per kilogram, which gives a coefficient of 0.62 for the kinetic friction on the surface. Example 8, a 120 kilogram beam is suspended in the air from a cable connected by a crane. The crane hoist is activated and the beam is set in motion. The beam starts from rest and, after it has moved vertically downwards by 12.5 meters, it is moving at 2.33 meters per second. Using the work kinetic energy theorem, determine the tension in the cable. Our free body diagram looks like this: tension, which is upwards, the force of gravity, which is down, and then it's accelerating downwards. We can see that because it's speeding up in this negative direction and it moves downwards 12.5 meters. So eventually we want to find the net force by using the net work equals the change in kinetic energy. So let's first use this in order to find the net force by noticing that, okay, our displacement is down and the net force must be down as well. I know that because it's accelerating downwards. So the net force is down, which means that we have cos of 0, which is 1. So the net work is F net d cos 0 equals Ke minus Ke naught, and Ke naught is 0. So we'll have F net d equals 1/2 m v final squared, and then we can find the net force, which is 1/2 m v squared over d. So that's 1/2 times the mass of 120 kilograms times 2.33 meters per second squared divided by 12.5 meters to give 26 newtons. That's the net force. It's always the net force that's in our work kinetic energy theorem. So now we need to find the tension in the string, and we will use Newton's laws to do that. So our net force in that y direction is equal to F net, of course, which equals Ft minus Fg. So let's be careful with this sign here. This formula gave us the magnitude of the net force, which is 26 newtons. In the y direction, that's downwards. So this is negative 26 newtons. And now we can solve for tension. So tension will be the net force in the y direction, or F net, plus Fg. So that's negative 26 newtons plus mg, 120 kilograms, times 9.8 newtons per kilogram, which gives a tension of 1,150 newtons.